Hi guys, again we're going over some examples of different models we can use to represent multiplication. So we're going to go over the tree diagram model. Now the example he used in class for this was Chipotle, if you remember doing the burritos here with the regular or just burrito bowl and then going through all these, showing this. So we're going to try to emulate this with a different example. I'm going to say sandwiches for mine. And let's say for sandwiches, I have wheat bread and I have white bread. So these are my two possible choices for bread. And from here, let's say that I have ham and I have turkey. And that means that white bread would also have the choice of ham and turkey. So the multiplication we're showing here is going to be 2 times 2 because we have two options and each two options has two more options, or a total of 4 there. Next, let's say I'm also adding cheese, and let's say I have provolone and cheddar. And let's see, a third, let's say I have Swiss. So from here, those would be my 3 choices for a ham. But also, I'm just going to use letters to abbreviate: provolone, Swiss, cheddar. Those would be my 3 options for turkey. Provolone, Swiss, cheddar would be 3 options for ham and white bread. Provolone, Swiss, cheddar would be options for turkey. So see, we're branching out here more. And then our multiplication method here would be times 3. So then if we did this problem, we should get the amount of possibilities we have. So 2 times 2 is 4, times 3 is 12, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's our amount of choices for the cheese. Hello again, everybody. Doing some review for our next breath mint. This breath mint is over chapter 4 currently that I'm working on. And I'm going to be going over 5 different methods for multiplication. There are a bunch of different methods. I'm just going to give you a quick list here so you can remember. We have physical manipulatives, which, remember, those are the blocks we used. Electronical manipulatives, we don't have access to those on the breath mint, obviously. So today we are going to be going over the geometric area model, FOIL, which is only in certain cases, the distributive property, which is the same thing basically as FOIL, vertical number decomposition, partial products, and the lattice method. So let's get started here with our geometric area models. So to me, the geometric area models are kind of just an organizational method for some of these mathematic problems. So let's do an example here where we have 18 times 42. And to do the geometric area models, you're basically just going to make some sort of rectangular shape. The size doesn't really matter. And you're going to decompose these numbers alongside here. So for the sake of making this problem easier, I'm going to say that 18 is 10 and 8, and that 42 is going to become 40 and 2 here. So then we would multiply each of these. 10 times 40 is 400. 10 times 2 is 20. 40 times 8 is 320. And then 8 times 2 is, of course, 16. And from here, we would just add these up along the side here to get our answer of 756. So this is just one model, the geometric area model for method for multiplication, I should say. Maybe we should cross that out. We should call it a method, because the models are those arrays and tree diagrams, remember? And these are the methods. So just a quick review of the geometric area model. Your steps for this are, number 1, you're going to decompose into hundreds, tens, and ones. Number 2, you're going to represent with rectangles to organize it. You're going to fill in the boxes and then add the areas together. All right, so our second method of multiplication that we're going to go over is the distributive property method. So this is the property that says we can distribute the groups differently here. So let's pretend we have the same problem, 18 times 42. And what we can do with that is the same thing that we did up here in the boxes with a decomposition, but it's in numerical form. So I could say that 18 is going to become 10 plus 8. See how that breaks down there? Decomposes is the word he's looking for. Decompose it. And I could say that then 42 could be 40 plus 2. And for this, we can pull out a common thread. And what I mean by that is we can say that this 10 plus 8 times 40 plus 2 is actually this equation, 10 times 40 plus 2, and, or plus, I should say, 8 times 40 plus 2. See how we did that here? We took this first number, 18, and now it's here. And we would, in essence, be multiplying each of the 10 and 8 by this same equation here. So that's why we have the 40 plus 2 and the 40 plus 2. And from here, we could break that down further. So we could say the 10 times 40 plus 10 times 2 plus 8 times 40 plus 8 times 2. And we could go further from here. So I've multiplied 10 and 40 and 10 and 2 to get 20, and 8 and 40 to get 320, and 8 and 2 to get 16. And this is the same kind of problem that we had right up here, where we added 40 plus 20, 420, add another 320 and 16, and so you're going to get 756. So the same answer again, which is perfect. That's what we want. So this is going to be our distributive property You can also call some of this FOIL, but remember that FOIL will not work for multiplication that has more than 2 digits each. So if you had a problem such as 330 by 120, the FOIL is not necessarily going to work with this, which is why we have the distributive property method. This one gets a little long, as you can see. So if you do come across a problem on the breath mint that's like this, and you have the option of solving it with something else, like the geometric area model or some of these other ones we're going to go over, I would recommend you do that, because the distributive property here is going to become really long and complicated. All right, so on to the next. All right, so for our next method here, we're going to use what's called the vertical method. And once again, we're employing the same number decomposition that we have done in our previous problems. So we're going to use the same example, 18 times 42. And what we're going to do to that is decompose these numbers into parts. So just like we did up there, I'm going to say 10 plus 8 would equal 18, right? And then I'm going to actually do 42 down here. So 40 plus 2. And you could break these numbers up differently if you wanted to. This is just the most simple way to show it, so that's why I'm doing it this way. So then next, we're going to set this up as this vertical multiplication problem. So I'm probably going to run out of room and have to start again, but we'll start here. We're going to multiply 2 times 8, which is 16. We're going to put our 6 here because this vertical method is all about organizing by place value. So this is our 6, and we're going to show our 10 group in the 16 over here like this. So we still have the number 16, but as you can see, it's very similar to up here. We're showing the 10s and the 6s. Next, we're going to go 1 over and show 2 times 10. And for here, we don't have any 1s. So we're going to say that we have 20 or 2 groups of 10. And that's showing our 10s place. So far we've completed this step here and this step here. All right, so I've rewritten the problem over here so that I have more space. We're going to go back now and we're going to do 40 times 8, which is 320. But we're not just going to write 320. We're going to keep our 20s from the 320 right here. And then we're going to add a new spot for our hundreds, which is 300 that we have. So once again, this vertical method is all about keeping those place values organized. Next, we have 40 times 10, which is going to be 400. So that means we have no 1s to write in, no 10s to write in, just 400 here. And from here, you add all these up in rows. So 6, we've got 50, and then we have 700, and you could add these together to get 756, which is perfect because that's the answer we've been getting in our geometric area model and in our distributive property model. We're going to do another model next. It is the partial products model. All right, so in our partial products method, I keep saying model, but we should call it a method, because remember, our models are only the arrays and the tree diagrams. These are methods of multiplying. So forgive me for mixing that term up. This is a method. For the partial products method, we're going to take this same number, 18 times 42, and we are once again going to set it up kind of similar to the traditional algorithm. So 42 over here, and then 18, but with one added step. This is the one where we're showing these multiplication steps on the side. So my first step in the traditional algorithm would be to say 8 times 2 is 16. So we're going to write that over here, 8 times 2. And our answer goes here. And here's the part that we need to remember. When we're saying 8 times 4, we're not saying 8 times 4, we're actually saying 8 times 40. So that's the part that's going to go over here, 8 times 40. And we're going to write that right here, which is 320, the answer to that right here. Moving on to our 1. Now remember, when we say 1 times 2, we're not saying 1 times 2, we're saying 10 times 2, which is 20. And when we're saying 1 times 4, we're not saying 1 times 4, we're saying 10 times 40, which is 400. And once again, these are the similar numbers that we've had in all our other end steps of the models. So we're going to add these up, 6, 5, the numbers are going to look very similar. 756, which is perfect. That's the answer we've been getting for all these other methods. So your steps for this one, set it up like a vertical method, give yourself some extra space over here, and you're writing out each multiplication step that you would maybe normally do mentally. You're writing it out fully, and you're not forgetting about the place value. That's the key here. You're not forgetting about the fact that this is actually a 40 you're multiplying, or that this is actually a 10. All right, so the next method we have here for multiplication is the lattice method. I'm going to be using the same problem, 18 times 42. Now, when you look at this box, you might think geometric area model. That's not what we're doing. We're going to do this lattice method, so you need your lines here and here. And this will work for 3-digit numbers. You would just have to make your lattice bigger. So we start by saying that the 18 is up here and saying that our 42, that our 42 is here. And then we're going to multiply. We have 8 times 4, which is 32. You're going to keep that separate, like so, 32. And then 8 times 2, which is 16. Once again, we're separating those tens and ones, kind of the same steps as we've done up here, just in a different form. And then we have 1 times 4, which is, of course, 4. I have no tens. And then we have 1 times 2, which is, of course, 2. Once again, no tens. Now you kind of add these up diagonally. So 6 plus nothing is 6. 2 plus 1 plus 2 is 5. And then 3 plus 4 is 7. And this is your answer here, actually, 756, which is perfect because that's the same answer we've gotten. So for the lattice method, remember, you're setting up your box with however many digits you have. So if you had 3 digits, this box would have a whole nother point here. You are doing your lattices diagonally, and then you're multiplying in each box and adding those up diagonally. All right, so now we are on to the final method we're going to use to multiply. And this is the traditional algorithm. Now on our breath mint review, he says that he wants us to know these 5 different methods for multiplication. And then one question he's going to ask that's related to the multiplication procedure that's taught and why there's a problem with this approach. I'm going to do my best to explain what I think the problem with this approach is, but I haven't gotten to talk to him about this, so take it with a grain of salt. So the traditional algorithm says that we set this problem up vertically, like so, and then we multiply 8 times 2 is 16, and we, this word that he hates, carry the 1. And here's where the traditional problem comes in, what I think. When we're telling students to carry the 1, they're not recognizing that this is actually a 10 group we're representing. They're seeing it as a 1. So then when they multiply 8 by 4, they're not recognizing that it's actually 8 times 40 plus 10. They're only seeing it as 8 times 4 plus 1. So when they do this, and then they add their 0, they don't know why there's a 0. They just know that they're supposed to. But this 0 is representing the fact that all these places we're about to multiply are actually 10 times something, which is why we have the 0 here, is because we're saying 10 times 2 instead of 1 times 2. So 1 times 2 is 2, 1 times 4 is 4, but remember what we're actually saying is 10 times 2 and 10 times 4. So that's why that 0 is there, because if we did add 10 times 40,